What is kurtosis? It is a measure of peakedness. It is a measure of peakedness or flatness of your distribution. How heavily the tails of a distribution differ from the tails of the normal distribution. That is what using kurtosis we can find out. And also the kurtosis is very much helpful to find out the outlier in your data set. Okay, here I'll just draw the thing here. For example, you have something like this. This is normal distribution. Okay. And you can see if you plot another data set, you will get something like this. Okay, you will get something like this. All of them are normal distribution. Okay, maybe my the way I draw is not correct. Okay, so all three distributions. So when the peak of the curve becomes relatively high, so this is the peak of the curve, relatively high. This is called leptokurtic. And when the curve is flat topped, then it is called your platykurtic. The curve is flat topped, like that, the peak is kind of flat. This is called your platykurtic. This one is called your mesokurtic. There are three types of kurtosis. One is leptokurtic, other one is mesokurtic, and platykurtic. If the peak is, the peak is too high, right? That is called a leptokurtic. The curve, the curve is flat topped, then it is called your platykurtic. If it is kind of a normal distribution, right? Normal curve is also called as a mesokurtic. Okay. But using kurtosis, we can find out how peaked. We are very particular about how peaked. We want to find out the peakedness of our distribution. Can we see any peakedness in my data set, or that is what we will be focusing on it when you plot the data set, right? In the distribution, when you see it, if you can find any peakedness, that is what your leptokurtic. So using kurtosis, we can identify whether the tails of a given distribution contain extreme values or not, the outlier. Okay. Look here, I put it here, mesokurtic, leptokurtic. You can see the peakedness is too high. And then you can see the extreme values here. And then here you can be flat top. And here it is something, here the extreme values are not much, but whereas the extreme value, because it's too peak, right? And you can see the extreme values here also. Here also you can see the extreme values. So here we are very particular how heavily the tails of a distribution differ from the normal distribution. This kind of a normal distribution, right? How heavily the tails of a distribution differ from the normal distribution. That is what we are interested in the case of kurtosis. Leptokurtic, like I said, the distributions with kurtosis greater, like Skewnes, you have some formula to compute the kurtosis. If the kurtosis value is greater than 3, it will have heavier tails than the normal distribution. This is your leptokurtic. Okay, and then see, by visually looking at the distribution, also you can find out, we can tell. Using sometimes it will be tricky. In that case, better you can use formula. The formula can help you to understand quickly whether it is a leptokurtic or mesokurtic or platykurtic. Distribution kurtosis is equal to 3, have the same tail thickness as the normal distribution. In this case, less than 3, if the kurtosis value is less than 3, it will have the lighter tails than the normal distribution. It has lighter tails, and even in this case, this kind of same tail thickness as the normal distribution, right? The leptokurtic will find heavier tails than the normal distribution. All the terms are fine. So okay, in the case of normal distribution, let's say in your Kurtosis formula, okay, I'll show you what is the formula. Using the formula, when you plug in the value and if you compute when you apply the formula, okay, with the values, if your Kurtosis value comes 0, that means normal distribution. Same as your Skewnes. In the Skewnes, what is the formula? 3 into mean minus median divided by standard deviation. The Skewnes value is 0 after you plug in the value. If that gives you 0, that means it is a normal distribution. Even in the case of Kurtosis, if you get the value 0 in the formula for the Kurtosis, that means it is a normal distribution. So this is what I have drawn. Okay, this is your normal distribution. This side is negative Kurtosis. Okay, and this is platykurtic and positive Kurtosis. Normal distribution. Kurtosis is used to find the presence of outliers in a data set. That is what we discussed. And now we will quickly take a look at a simple case study in the case of Kurtosis. Okay, how the Kurtosis is helpful in the real world scenario. Let's consider a problem faced by a food processing company. Listen, they use two machines to produce or to fill the packets with snacks. So these are the machines, these are the machines they are using. These are the snack packet, okay? These machines fill these packets automatically, okay? The target weight for each packet is 500 grams. So this machine should fill each packet with 500 gram capacity. It should not fill more than 500 grams. It should not fill less than 500 grams. If it fills less than 500 grams, it will damage the reputation. The customers will complain. You mentioned 500 grams, but when we unpacked it, we could see that only 450 grams is there. If you fill it more, if the machine fills more, mistakenly or due to some issue, if the machine fills more, what will happen? It will shoot our cost, right? As a business owner, I'm going to lose. If each packet, if you fill additional 100 gram, the machines mistakenly, if it fills 100 gram in excess, let's say every month we sell 100,000 packets, 1 lakh packets we are selling every month. Per packet 100 gram, if you multiply 100 into 100,000, it is going to be a huge loss. Overfilling, underfilling is also a problem. In this case, the problem posed by the manufacturing companies or the company is the machine A is an older model. Let's assume that this is a machine A, it's an older model. It seems to produce a high number of packets that are significantly underweight or overweight. Sometimes, this machine fills some packets with more, it fills with more volume. In some packets, it fills less volume. Let's assume that some packets it fills 600 grams, some packets it fills 400 grams only. Okay, so this is a new machine. This machine consistently produces it consistently fill the quantity in each packets close to the target. The target is 500 grams. Somewhat close to 500 grams it fills. There will be variation because the machines are filling. Still, there is a little bit variation, but it should not be like this much. So this is the problem posed by this manufacturing company. Okay, and now the question is how we are going to solve this problem. We can calculate the kurtosis of the weights of both the machines. If the machine A has significantly higher kurtosis than the machine B, this will give us the quantitative evidence that the machine A is overfilling, or it has some inconsistency. It is not filling correctly. Machine A has more extreme outliers. Either it overfills or it underfills, 600 gram or 400 gram. Ideally, it should fill 500 gram. If it is minor variation, 503 gram, 498 gram, it is fine. But it is, if it is overfilling and underfilling, it is a problem. So using kurtosis formula, if you find out a higher kurtosis, right? So the machine A has significantly higher kurtosis than machine B. So this can give us the quantitative evidence that the machine A has more extreme outliers in it. More extreme outlier, that means, it has some issues. On the one hand, it is overfilling it. On the other hand, it is underfilling it. With that itself, we can make out. So this is what the problem they want us to solve. The company needs to quantify these observations. Let's say you randomly sample some packets and then you want to test it. The company plot it, right? The company needs to quantify these observations to understand if there's a significant difference in the performance in the two machines. So this is the formula for your kurtosis. Subtract the mean from your each and every value, and then you need to square. So you need to 4 times you need to square it, right? So you need to raise 4 times this value after subtracting the mean from your each value. You need to raise this to 4 times and into n divided by, this is the formula you need to use it. The kurtosis value is more, then you have higher extreme values. You have more extreme values. If the kurtosis value is 0, that means it's a symmetric distribution. Symmetric distribution. Okay. So the kurtosis, the values will always be positive or 0. So that is what I compared the difference between Skewnes and kurtosis. In this case, when we come back here, if the kurtosis value, for example, if you have the data set, right? Let's say you have taken randomly 100 packets and you ask the people to unpack it, you open it and then weigh each packet quantity. Some packet you have 400, some packet 450, some packet 600. You take everything, right? You take all the data and then plug in the value. You can, let's say you take 100 packets. That 100 is nothing but the n, number of packets. And find out for the 100 values, the mean value. Subtract the mean from each and every value. For example, 400 minus, let's say your mean value is 500, minus 100 to the raised to the power 4 into 100 packet divided by, you need to plug in this value. If you plug in this value and if the kurtosis value, the kurtosis value ranges from 0 to infinity, whereas in the case of Skewnes, it ranges between minus infinity to plus infinity. The Skewnes value is negative, that is left skewed data. If the Skewnes value is positive, it is a right skewed data. The Skewnes value is 0, then it is symmetric. Whereas in this case, the kurtosis value is 0, that means Skewnes. If the kurtosis value is very high, then extreme values are there. If the kurtosis values are not so high, relatively less, then it is, it's kind of a, it's okay. Okay, not much variation. We don't see, extreme outliers. Okay, very high and low and 0. There are 3 values. You can see it here. Okay. Here there is no negative here in the case of kurtosis. Always positive or 0. Can be positive or negative in this case. This is the formula. This is a measure of the asymmetry of a distribution, measure of the peakedness. Here we are very much interested in finding out the peakedness. Can we see any peakedness or flatness are there in the given distribution? Okay. So if the value is more, you can say that this machine has some issue. Now you can argue one thing with me. You can tell me, with this example, right? Whatever I quoted, whatever the one I gave it, with this itself, you can tell. Machine A, you said already it is overfilling and underfilling. Then why the hell do I need to plot this, and why do I need to, spend time in finding, use and kurtosis and calculate the kurtosis values, everything. Why should I do that? That's a good question. Okay. So see, when a company, right, when they observe that machine A seems to be less consistent than machine B, it is based on the, the anecdotal evidence. See, just because some machine, right, listen, two machines are there. These two machines can also have some kind of variation, right? Even though it is a new, there will be some kind of variation. Let's say this machine, in some cases, it is, the variation are not much. So sometimes it feels 500, 503. And when you take a few packets, right, you can see 500, 503, 510. And here also 500. But some packets, just because one or two packets, for example, even this machine also can overfill, underfill in some cases. Okay. So there are only based on few observation itself, we can decide, we cannot decide this machine is bad. The whole idea is we need to, let's not go by our guesstimate or based on whatever we see. Everything should be the decision, whatever we take, it should be data driven. The data, and then you use the formula and then you compute it, and then you tell, yes, machine A is inconsistent compared to machine B. Okay, that is what. So this is one of the simple thing, but many of them they get stuck up with this one. Okay, when they explain to the stakeholders, they get stuck. You can tell them the decision should be data driven. It is not data driven based on the evidence only. We need to conclude. So this is the formula. That's the reason why in starting they came up with many different formulas, right? With that we can conclude. And the thing, what are the other common use cases where we can use the kurtosis? In the case of bank, they might use kurtosis to assess the risk of its loan portfolio. Say high kurtosis indicate that the portfolio is more likely to they experience extreme losses, which can lead to financial problems to the bank. When the high kurtosis value is very high. And in the case of hedge fund, right, the hedge fund might use kurtosis to choose investment that have a high potential for returns, but also a low risk of extreme losses. Right, with that we can make a decision. Right, we can make a go no go decision. Go no go decision. Whether I can go ahead and invest on this specific hedge fund or not. By looking at the distribution itself, you can decide. And also it is a regulator, right? The regulator might use the kurtosis to set limits on the amount of risk the financial issues that can take on, okay? To summarize, kurtosis is a measure of peakedness of distribution. A distribution with high peakedness, right? Distribution with high kurtosis, we can say it's a leptokurtic. And a distribution with low kurtosis is said to be platykurtic, which means it has a low peak and thin nails. A distribution with kurtosis equal to 3 is said to be mesokurtic. It's kind of your normal distribution. So in the case of mesokurtic, your peak is neither too high or nor too low, and also the tails that are neither too fat or nor too thin. These are the things you need to remember. It is very simple one, isn't it? But the advantages are manifold when you use these kind of things in real world scenario. Okay, now let us have a quick question around the Skewnes and kurtosis. What is the difference between Skewnes and kurtosis? What is the difference between these two? All of you, please type it in the chat window. Skewnes will help us to understand the asymmetry of the data, whether it's a normal distribution or it's a right skewed or left skewed. Whereas in the case of kurtosis, we are very particular about the peakedness of the data. If the kurtosis value is very high, that means leptokurtic. If the kurtosis value is less, then it is your platykurtic. If the kurtosis value is 0, then it is normal distribution. Okay, how the kurtosis is calculated? The formula they will ask. Okay. And what are the other questions you can expect? Yeah, these are the things. If you know, as of this, right? This is enough. And with this, I'm